When light hits a surface, it's reflected back into our eyes, and that's how we actually see it. When light shines on a shiny surface, however, again it's reflected back into our eyes, but we see an image behind the shiny surface. It appears to be within the mirror. If we fire a light beam at a mirror, it's reflected back from the mirror. We can create a line perpendicular to the surface of the mirror, which we call the normal. Then if we measure the angle between the incident ray and the normal, we call this angle the angle of incidence. When we measure the angle between the reflected ray and the normal, this is called the angle of reflection. For a plane mirror, it turns out that the angle of incidence is always equal to the angle of reflection. Can you explain why windows in distant houses appear to reflect the sun only when it's rising or setting? Think about it for a minute. When the light beam hits the window from the setting sun, it's reflected directly back into the eye of the observer, making sure that the angle of incidence is equal to the angle of reflection. However, during the heat of the day, the sun is much higher in the sky, and when the light strikes the window, the reflected ray goes down towards the ground and it's not reflected back into our eye, and hence we can't see the image of the sun as it's high in the sky. You often find bike reflectors on the back of a bicycle to make the rider more observable to people in cars. The reasons these work is because the headlight beam from the car behind strikes the reflector, and making sure that the angle of incidence is equal to the angle of reflection, the ray is reflected vertically. It hits the other surface of the reflector where the reflection occurs again, and it reflects that incident light ray directly back into the eyes of the driver, and consequently the bike can be easily seen. So why do we see the image behind the mirror? When the light from the object is reflected from the mirror, the incident ray is reflected back into our eyes, making sure again that the angle of incidence is equal to the angle of reflection. However, we think that light travels in straight lines, so we think that the image actually is in a straight line from the way we are looking, and that means that it appears to be behind the mirror, an equal distance behind the mirror to where the object was in front of the mirror. We can make use of this property of reflection in objects like optical fibres. If we take a light beam, we can arrange the diameter of the tube of plastic or glass or whatever it is, so that when the beam strikes the surface, it is reflected back and hits the other side of the glass tube. This continual reflection backwards and forwards allows the light to travel along the tube very, very fast because it travels at the speed of light. This is the basis for optical fibres, and these are used in telecommunications because the light travels along very, very fast. You also see this sort of thing used in fantasy lamps, like the one shown on the right, where the light beam is down at the bottom of the lamp and the light is totally reflected inside the plastic tube until it appears at the end. The images we see in a mirror are not superimposable with the object itself. You can see from this girl's shirt the reflection of the H of hate actually is in an inverted image, or what we call a mirror image. Just study it for a minute and see if you can work out how it's set up. Convex mirrors are a little bit more complicated than plane mirrors, but we can still locate the image quite easily if we draw a simple ray diagram. If we take a beam of light emanating from the top of the arrow, it hits the mirror. We can draw in a normal at this point, at right angles to the surface of the mirror, and the reflected ray is reflected back such that the angle of incidence is equal to the angle of reflection. If we take another beam coming from the top of the arrow and make it pass down so that it hits a point on the mirror level with the base of the arrow, then that line that connects the base of the arrow to the mirror is our normal, and we have a reflected ray coming off where the angle of incidence and angle of reflection are the same. Now if we trace those reflected rays behind the mirror, the point at which they intersect must be the top of the arrow, since the incident beams both came from the top of the arrow. So our image appears behind the mirror, and the object appears, or the image rather, appears to be smaller than the object that it came from. Another advantage of convex mirrors is if you look at those reflected rays, if we reverse the direction and make them the incident rays, you can see that the light comes from wide out and is reflected back to the top of the arrow. In other words, it gives you a much wider field of view than, say, a plane mirror does. We can put this to use in quite a few situations. One of the practical uses for convex mirrors is in road safety. You might have seen mirrors like this on the side of the road. You can see the one with the orange cap on it there actually gives you a much wider field of vision because it's taking light rays from a lot further away and reflecting them back into your eyes. Similarly, the side mirrors on your car give you a much wider field of view of what's behind you than it would if you had a plane mirror there. Images that appear in concave mirrors are a little bit more complex than plane mirrors or convex mirrors, so we'll just concentrate on one specific case. If we take a concave mirror that's shaped like a parabola and we fire an incident ray at it from a distance, then that ray is reflected back from the mirror and crosses over the median line. If we take another ray from the distance and reflect it back, it crosses that ray over at a particular point. And it doesn't really matter where the incident ray comes from, the reflected ray will always reflect back through that point. We give that point a special name. It's called the focus of the mirror, and it depends on the curvature of the actual mirror. If we repeat this experiment and use a semicircular mirror rather than a parabolic mirror, it still has a focus, but the focus actually moves depending on where the light ray comes from. So that means that you don't get a very sharp focal point with a semicircular mirror like you do with a parabolic mirror. That means that we can use these parabolic mirrors in quite a few industrial situations. So for instance, if we have a radio telescope, if we put the detector at the focus point of the parabolic dish, it means that any radio signals that come in from outer space are reflected back and amplified at the detector point, and they're detected and then sent through to the computer for analysis. Similarly, if we use a solar catcher, that's what we're wanting to collect the rays from the sun, those sun rays hit the shiny surface and they're reflected back to the collector, which is set at the focus point, and that will collect all the heat. In fact, if you did this on a small scale and you put a sausage or something like that there, you could actually cook the sausage by putting it at that point.